A ball is dropped from the top of a cliff. 1 second later, a stone is thrown vertically downwards. So the ball is dropped first, and after, please, when you don't mute yourself for me, okay? The feedback. So the ball is dropped first, and 1 second later, a stone is thrown vertically down from the top of the cliff at 15 meters per second. The ball and the stone hit the sea at the same time. Find the height of the cliff. Okay, so both were actually dropped from the same height. But the difference is that they were not dropped at the same time simultaneously. The ball is dropped first, then followed by the stone. One second later, the stone is dropped. So write an equation for the ball, write an equation for the stone. So for the ball, let the time taken for the ball to be dropped, okay, be t. So let the time taken, or let t represent the time taken for the ball to be dropped. So please, if you haven't muted, please do so for me. The 3 seconds. And the ball is dropped, free falling. So it means that u equals 0. Oh, the network isn't helping. U equals 0. So if u equals 0, then h, which is equal to, please, this is vertically downward motion. I saw a lot of you treating it as vertically upward motion. No, it's a vertically downward motion. So because u is 0, we have the height of the cliff given us half times gravity was given as 10 meters per second squared. Therefore, the height of the cliff is equal to 5t squared. And let's take this to be equation 1. Okay. Then for the stone, an equation for the
Yes, mommy.
I can mute yourself. Before today, the network isn't helping at all. But I'm sure as we move along, it will stabilize. Okay. Okay, so we have the equation for the stone. The equation for wow. Hello. Yeah, it's a network problem coming. Okay. So let's try for a while. If it continues like that, you'll see what to do. So in the meantime, let's try. Class, are you okay?
Yes, sir.
If it continues, I'll work things out and then we'll see what. It's not even allowing me to write. So whoever is having challenge at his or her end is actually due to a network problem. Okay. All right. So the equation for the ball, we have h equals 5t squared. I hope you can see and you can hear as well.
Yes, please.
Yes, sir.
For the stone, we are told that 1 second later it was also thrown. 1 second later, a stone is thrown vertically downward. So if the time taken for the ball to be dropped is t, what will be the time for the stone? Yes. If the time taken for the stone ball to be dropped is t, what will be the time taken for the stone? Class, quick one. Gideon, go ahead.
T minus 1.
So t minus 1 is the time taken for the stone to be dropped. And so therefore, h, I'm coming. Okay, and so h, which is equal to ut plus half gt squared. Now this time around, the ball is thrown with a certain initial velocity from up the cliff, 15. So 15 times x time, which is t minus 1, plus half times 10 times t class. If it comes the worst, we will push this class from 6:30 to 8:30 as we've done before. If it comes to the worst case scenario, okay? Because I think today's network is a stubborn network. It doesn't want to cooperate. Okay, so we have equation for the ball, h equals 5t squared. Then for the stone, we have h equals 15 times t minus 1 plus half times 10 times t minus 1 squared. And when we simplify this, we have what is left. We've done the physics part. What is actually left is the mathematics part. Okay. I hope you can hear me. Are we there? Hello, class. Do we
I say.
Yes, sir.
hey, let me pick the view of all. Do we push this class for the evening?
Yes, please.
Because it looks as if
Yes.
this morning's network wouldn't help. Can we Daisy, we want to push it for 7 or 6:30 to 8:30 so that it I'm sure the time from 6:30 to 8:30 will help us, because the problem is that the network situation seems to be disturbing us. I can't assure if it's going to be stable within about 30 minutes from now. Okay, I can try, but the point is that you try along the line, it comes on and then it goes off again. So when it's that intermittent problem, following becomes difficult. Sidel and Co. I'm using I'm also using MTN. Telecel, unfortunately I don't also have a ported Wi-Fi. That's the problem. I can try, but the concern is that it will come on, go off again, and following becomes a problem. Let me try for the last time. Okay. Hello, is that clear? Can you hear me? Class, can you hear me out? Hello.
Yes.
Emelda and Co, can you hear me?
Yes.
Yes, sir.
It's the network. So please, if it continues like this, you must sympathize with me. Okay? Because it's because of the network issue. I wish I even do it and then wash my hands off it, but the problem is the network. So this is for the ball. This is for the ball, and then the stone, we have H equals 15 T minus 1 plus half times 10 times T minus 1 squared. When we expand, we have 5 T minus 1 squared is T squared minus 2T plus 1. So let's expand everything. 15T minus 15 plus 5T squared minus 10T plus 5. So that when you simplify 15T, okay, 15T minus 10, that is minus 15 plus 5, minus 10. Okay, minus 10T plus 5T squared. Then when we properly group like terms, we have 5T, 15T minus 10T minus 10 plus 5T squared. Now, since the ball and the stone were thrown from the same height, H for the ball, H for the stone, the same. And so we equate 5T squared to 5T squared plus 5T minus 10. We have this side canceling out to 0. And so 5T is equal to 10. Therefore, T equals 2 seconds. What does it mean? Earlier, we said that let the time taken for the ball to drop be T. So if we have T is equal to 2 seconds, then it means that it took the ball 2 seconds to drop. What about the stone? If the time, hello? Hello? Oh, I'm listening. Oh.
Please, I don't understand.
I'm coming. No, it's because we have, in fact, I derived the first part of the equation. I'll go over. So you let's finish. Then we said that
Please, I am new.
okay. It's unfortunately it's because we started this topic way back, so we've lost the foundation, the beginning part. Please send me a WhatsApp message after the class so that I can send the video, the first videos to you. Okay. So, I mean, those of you who are new, okay, should give me the message. So it took the ball 2 seconds to drop, and it will take the stone. Don't forget the time for the stone. We said let the time be t minus 1. And so the ball will take 1 second. Sorry, the stone will take 1 second to drop. Okay. And so once you found the time for each one of them, if you take the equation for the ball, which is h equals 5t squared, and substitute, you have the height of the cliff. So 5 times 2 squared, which is 5 times 4. This is 20 meters. If you take the equation for the stone, which is h equals 15 t minus 1 plus 5 t minus 1 all squared, you must get the same height. So 15 times 1 plus 5 when you expand this, don't forget this is t squared minus 2t plus 1. So when you expand and you put in the value of t, you have this is 0. When t, let me take my time, and then t being 1 squared minus coming in. It's not easy. Today's network is actually whipping me up or flogging me. It hasn't been like this. I don't know why today things are not turning up. All right. So our h is equal to 20. Whether we use the equation for the ball or the stone. Class, are we okay? Are we okay?
Mister.
I want us to also look at the second question. The second question, because that is a bit deep. And I want us to look at deeper questions when it comes to this. And I'm reading the last question I forwarded to the group to be tried. 2 particles, P and Q, are shot vertically up. Particle P is first up with a velocity 40. So if we pick particle P, for P, it is shot with an initial velocity of 40. 40 meters. After 4 seconds, particle Q is also shot up. So they are all shot from the same level. Let's assume they are all shot from the ground level. So particle P is shot first. Then after, this is shot with an initial velocity of, let me bring the diagram here at the other side. With an initial velocity of, this is P, of 40 meters per second. Then 4 seconds later, particle Q is also shot. And we are asked to find where the two particles meet. If at the point of meeting, P has a velocity of 15 meters per second. Now, class, the two particles would only meet if P gets to the maximum height and it is returning. Then, during the time where Q also goes up, then they would meet each other. This is because they are all thrown vertically upwards. So the only condition where they can meet is that the first one, which was shot earlier, must reach the maximum height and then be returning to the ground. Then it will meet Q. Class, are we okay with this explanation? Class, are we fine?
Yes, sir.
Yes.
And this is because they are all thrown vertically upwards. So once they are all moving in that direction, one must go up and then be returning. Yes, Saki, your hand is up. Saki.
Please, I didn't get the explanation well.
They are all thrown vertically upwards. So once they are all moving in the same direction, they cannot meet. As in, I am coming and you are going. It means once I'm coming, okay, coming from one direction and you're also coming from the opposite direction, we can possibly meet. But here is the case, they are all thrown to go up. So they can only meet if one has gotten to the maximum height and it is returning back from where it is thrown. Saki, that's what I'm saying. Are you okay? So for them to meet, P must get to the maximum height. And then from the maximum height, when it is returning, let's assume as at when they actually met, P is here. Then, because they are not thrown at the same time, Q can also be here. So I'm assuming this is the point where they are meeting each other. One has a direction downwards, and the other one also has the direction upwards. So they can only meet at this condition. Are we okay?
Yes.
What it means is that we must find the maximum height P gets to. Class, please help me determine the maximum height that can be reached by P. Maximum height that can be reached by P.
Yeah.
So H is equal to, is vertically upward. So U squared over 2J. Therefore, we have 40 squared over 2 times 10. And this is giving us 1600 divided by 20. This is giving us a height of 80 meters. Are we okay? Class, are we okay?
Yes, please.
Now,
Yes, sir.
help me determine the time taken to reach the maximum height by P. Time taken to reach the maximum height. Just calculate and tell me.
Sir, it will be 4 seconds.
Okay, so we have 40 divided by gravity, 10. And this is 4 seconds. Good. So now at the maximum height, final velocity is equal to 0. So we are also told that at the time where P meets scale, the final P has a velocity of 15 meters per second, meaning that at this point where P meets particle Q, velocity of P is 15. So if at the maximum height velocity is 0, and at this point velocity is 15, then we can determine the time taken for P to meet Q. Meaning we determine this time taken for P to reach a velocity of 15. Meaning over here we have initial velocity 0, and at this point velocity is 15. So we can calculate for the time where P meets Q. Class, do that for me. So when P is falling downwards, when P is falling downwards from the maximum height, this is also the same as when P meets Q. When P meets Q, the time taken for P to fall from the maximum height to the point where it meets Q can be obtained using V is equal to U plus GT. V is the velocity at the time where P meets Q. Class, calculate that for me. V is the velocity where P meets Q. So we have Gideon, let me take over and then so that the rest can follow. So 15 is equal to 0 plus 10 times T. Please mute yourself if you haven't. Caleb, mute yourself for me. Therefore, T is equal to 15 on 10. And this is equal to 1.5 seconds. So class, my question is that what is the total time taken for P to meet Q? Total time taken for P time.
I'll try. I'll try. Mama, Jeff, what there? Mama, Jeff, what there? Mama, wrong podcast is at 1 o'clock.
Let me mute all. Gideon, what's the total time taken for P?
75.5 seconds.
For P to meet Q.
75.5 seconds.
Exactly. So class, it is equal to 4 seconds taken to reach the maximum height and plus 1.5 seconds taken to move from the maximum height to meet Q. So the total time will be 4 plus 1.5. And this is equal to 5.5 seconds. Plus, what it means is that by the time P meets Q, P has traveled 5.5 seconds. If by the time they meet, P has traveled 5.5 seconds, what will be the time for Q to meet P? What will also be the time for Q to meet P? If by the time they meet, P has traveled 5.5 seconds, class. So time taking, Frank.
To be the maximum height minus the time taken for P to get to Q.
Frank, listen to the question. If by the time they meet, P has traveled a total of 5.5 seconds, what will be the time traveled by Q by the time it meets P? That is my question. Frank, that's my question. So time taken for Q to meet P. Yes, anybody? Gideon, let somebody else answer. Yasmin.
So it will be 4 minus 1.5.
Yasmin, why 4 minus 4? Why 1.5?
Because the maximum height from of P, the maximum height of P is 4 seconds, and then the time for the P to move downwards to the same level with the Q is 1 second. So you subtract.
No, it is 1.5 seconds.
1.5 seconds. So subtract.
Yasmin, you've done well, but let's listen to somebody else. Because you are missing something. Okay, Frank, let's also hear what you have to say. By the time Q meets P, what will be the time, okay, taken by P, by Q?
It will be the time taken for P to reach the maximum height minus the time taken for P to reach Q. It is minus because Q is moving in an upward motion.
Listen to the question. Class, listen to. You are forgetting something from the question. Two particles P and Q are shot vertically up. Particle P is first up with a velocity 40 meters per second. After 4 seconds, particle Q is also shot up. After 4 seconds, particle Q is also shot up. So my question is that if by the time P and Q meet, P has traveled 5.5 seconds, what will be the time taken for Q to meet P? That's my question. Q must travel a time of what to meet P? If by the time they meet, P has traveled 5.5 seconds. Yasmin, over to you.
So it will be 5.5 minus 4 seconds.
Exactly, because in terms of time, P leads Q by 4 seconds. So by the time they meet, Q will travel at a time of 5.5 minus 4. Minus 4. So this is the time taken for Q by the time they meet. So this is actually 1.5 seconds. Class, are we okay? So by the time they meet, P has traveled 5.5 seconds, but Q has traveled 1.5 seconds. By then, this is first part. Let's look at, by the time they meet, what is the total distance traveled by P? Somebody to help me. By the time both particles meet, what will be the total distance traveled by P? Yes. Anybody? Don't forget, we have the maximum height. We have the maximum height. That is equal to 80. Then what will be this distance? By the time they meet, P must travel this distance from the maximum height to where both are meeting. So what will be this distance? What will be H? When we determine H, then we can be able to determine the distance, the requirements of question 1. Question 1 says that find where the two particles meet. If at the point of meeting, P has a velocity of 15 meters per second. Okay, let me come in. So let's determine, Saki, juniors.
Service, I got 4.5 meters.
4.5. Let's see. So using H equals UT plus half GT squared. U is 0. I mean for P. So half times 10 times the time taken to travel from the maximum height to where they meet. That is 1.5. So 1.5 squared. And this is 5 times 1.5 squared. Class, what is 5 times 1.5 squared? Square 1.5 and multiply by 5.
11.25.
Come again.
11.25.
11.25 meters. So if by the time they meet, P has traveled 11.25 meters from the maximum height or from the top, then what will be the distance they've traveled by the time they meet? What will be this distance where they will meet? Don't forget, the maximum height is 80. So when we subtract 11.25 from 80, then that will give us where the two particles would meet. Don't forget, our measurement is from the ground. Okay. Our measurement is from the ground. So if this is equal to 11.25, then the remaining distance, Imelda, are you there?
Yes, please.
Either go Anna. Today you people are quiet. So what will be this distance? From the ground, yes.
Say 80 minus 11.25.
Which is?
68.75.
Yes. So 80 minus 11.25. And that's equal 68. 68 point what?
75.
Meaning that the two particles will meet at this point or at this height. 68.75 meters from the ground. Please, are you okay? Then the last question. The last question, find the velocity with which Hill is shot, the initial velocity of Hill. That is easier because H is equal to UT minus half GT squared when Hill is going up. And by the time they meet, Hill must travel 68.75 meters. 68.75 meters. So 68.75 is equal to U is not known. That's what we are looking for. But what is the time taken for Q to meet P? By the time they meet, what is the time traveled by Q? Yes.
1.5 seconds.
That is 1.5. Minus half times 10 times 1.5 squared. So we have 1.5 U plus 5 times 1.5 squared. And more, that was 1.5 squared.
2.25.
2.25. So help me determine the value of U. Help me determine the value of U. Oh, sorry, please, this is minus. This is minus. Let me correct it. And I'm sure you understand why it is minus. Q is going up. So what's the value of U? Anita, are you there?
Yes.
21. What's the value of U? Hey, nobody is calculating. Anita, you are not calculating. Emelda, you are not calculating either.
7.051.
Just 7.
7.051.
Check, I doubt. 68.75 plus 11.25 divided by 1.5. We are looking for you, don't forget.
$53.3.
Yes, that's the answer. 53.3 meter per second. That is the initial velocity of Q. And please, yes, I think this is a very good work because you do not expect to be solving simple questions all the time. You must solve brainy questions which would excite or elicit some level of thinking from you. Okay, so please note the step-by-step way of solving the question, understand it, and then what you can do to master the tricks is that at an appropriate time, drop the question somewhere. The solution. Pick the same question and try solving it without looking on anything. You'll be good to go. Giovanni.
Sir, please, the minus half GT. Is it because you are calculating for the initial velocity of it going up?
Come again, minus.
Sir, please, when we were finding for you, is it the initial velocity of the ball moving up?
Yes, of Q. The initial velocity of Q. And it is minus because the ball is going up. Godfrey.
Sir, please, what is the topic?
What is the
topic for this question?
Oh, this is vertically upward motion. Yeah, motion under gravity. Okay.
Sir, please, can you send me the videos?
I will. Just give me a message after the class. Okay.
Yes, please.
And you must request for another brainy kind of question from me. Just try it and then send your solutions to me. I will just mark it and then draw your attention to where perhaps you went wrong and all that. So I encourage you to be attempting challenging questions like this. Okay. As for the question 2, it is not difficult. I wouldn't want us to waste our time on the question 2 because once you are good to go with this, you can easily solve the question 2. Please, if you have any question, ask before we continue. Valerie, Pokua, Yasmin, JD. Ask your questions if you have one. Okay. If there is no question, then we want to move to a new topic. That is fluid mechanics. Fluid mechanics. That is where there is a story of Archimedes' principle. There is a story of upthrust and all that. So fluid mechanics is our next topic. What is density? What is density? Yes. Anita, what is density?
Sir, please, the mass per unit volume of a substance.
This is true, but what does it mean? The mass per unit volume of a substance. Anita, what does it actually mean? Elika, you're also there. Can somebody share?
A measure of how much?
Come again. Yeah, Bogua, come in.
Density is a measure of how much mass is contained in a given volume.
What is mass? What is mass? Yes.
Mass is the amount of substance contained in matter.
What is amount of substance? Gerald,
Sub is mole.
what is mole? Okay. All right. So what we know is that all substances are made of particles. Okay. So when we talk about the amount of substance, we are referring to the amount, the number of particles that actually come together to make the thing up. So mass is about number of particles within a given volume. For the same volume, if we have this volume and then another same volume, but we have few particles in here, and we have more particles, the same number, the same size, but over here we have more. Then we can say that A, this is A, this is B. The density of B is greater than the density of A. This is because mass of B is greater than mass of A for same volume. Is that okay? And so we say that for the three states of matter, which one has the greatest density? For the three states of matter, which one has the greatest density? Class, I'm listening.
Solid.
State.
Solid because there are more particles that are closely packed than liquids and also than gases. So density actually refers to number of particles within a given volume. And this number of particles is what we call as mass. And so density is directly proportional to mass, provided volume is constant. Volume is constant. When volume of two bodies does not change, you have density being directly proportional to mass. And class, when two quantities are said to be directly proportional, what does it mean? When two quantities are said to be directly proportional, what does it mean? Giovanni?
Meaning the higher one quantity, the more the other quantity is.
And you have the idea. Elikem. Giovanni, another hand is up. Please go ahead and share with us.
They are the same.
Sorry, they are not the same. Anita.
Sir, please, it means if, let's say, if one is 2, the other one will be 2, like they will have the same value.
No, Anita, I won't buy. Frank, last one.
It means if one is increasing, the other one is also increasing. And if one is decreasing, the other one is also decreasing.
This is what it is. When two quantities are directly proportional, it means that an increase in one results in an increase in the other. And a decrease in one also results in a decrease in the other. So Density is directly proportional to mass, provided volume is constant, meaning when mass increases, density would also increase. And when mass decreases, density would also decrease. So, for two different masses, you must have different density. So, rho 1 is directly proportional to M1, and rho 2 must also be directly proportional to M2. When you take ratio of rho 1 over rho 2, this must be equal to M1 over M2. And you can use this to calculate for the density when the mass changes. Okay, I'm going to set an example. The density of a given mass M is rho. When the mass is doubled, what will be the density? So the density of a given mass is M. The density of a given mass M is rho. When the mass is doubled, what will be the new density? Or what will be the density? Yes, Elikem.
2p.
The symbol is rho. It is pronounced as R-H-O, rho. Okay.
2
rho. So let's see. For M1, the density is, for M, the density is rho. Now, if the mass is doubled, 2 times the initial mass, what will be the new density? We don't know. So using rho 1 over rho 2 is equal to M1 over M2. M1, the first mass, we have rho over rho 2 equal to M over the new mass is 2M. And M and M will cancel. Therefore, we have rho over rho 2 is equal to 1 over 2. Make rho 2 the subject, and rho 2 equals 2 times the initial density. Okay, so density is directly proportional to mass, provided density volume is constant. Then, please, is there any question? Then, the same density is also inversely proportional to volume on condition that mass is constant. If mass is constant, here what it means is that imagine we have the same number of particles in 2 different containers. Let me clear and then indicate another one. Anna, are you here? Anna.
Eh.
Priscilla, are you here?
Yes, sir.
Okay, so we have two different containers. A smaller one and then a bigger one. We have the same number of balls. X number of balls. Of the same sizes. Even though we have the same mass, the same number of balls or particles, but because their volume are not the same, we cannot say that their densities are the same. So density is inversely proportional to volume, provided mass is constant. And when two quantities are said to be inversely proportional, Frank, let me ask one of the ladies. Priscilla, what does it mean? If two quantities are said to be inversely proportional, what does this statement actually mean? Priscilla. Hey. Our Priscilla is not there. Anna, Anita.
Sir, please, as one quantity increases, the other decreases, and vice versa.
So as one quantity increases, the other decreases, and vice versa. It's true. So it means that if the volume increases, density would decrease. And if volume decreases, density would increase, provided mass is the same. So over here, in our two illustrations, the density here, density of 2, row 2 is less than row 1. But it will work on condition that the masses is the same. Is that okay? So density is inversely proportional to volume. When you increase volume, you decrease. Can you give me another two physical quantities that has such relationship? Giovanni, two physical quantities with the same relationship.
Except is distance and time.
When
sorry, except this distance and speed.
No, it's not distance and speed.
No, sorry, it's speed and time.
Speed and time. Speed is inversely proportional to time. More example.
Sir, please, I have a question.
What's your question?
So say if there's a chance where the mass is not constant between the two objects or quantities, can it be that density is proportional to volume?
Then it's not a fair assessment. Okay, it's not a fair assessment. Look at these two situations. Imagine you have 10 balls here and 15 balls, and the volume two are not the same. then you can say that easily say that the density of this is maybe greater, or you see, before you can make a better judgment, you must give them the same condition. And the condition is that for density and volume, you must give them the same masses. And for density and mass, you must give them the same volume. If you don't give them that same condition, it isn't a fair assessment of the two situations. Are you okay? Hello, are you okay? Okay, Gideon, your hand is up.
Yes, sir.
Energy and work.
Energy and work.
Except it's temperature and heat.
Temperature and heat are what?
Are also proportional.
Okay, I'm talking of inversely proportional. Pressure.
Yes, sir, they're also
inversely proportional. We can also talk about pressure and area. Pressure and area. When area increases, pressure decreases. And when area decreases, pressure increases. Frank.
Sir, please, I have a question.
Okay, ask.
Sir, please, so what's the constant value for mass in if pressure and what's the constant value for volume if pressure and mass are directly proportional?
Hey, Frank, what I mean by mass being constant is that you should give them the two different volumes the same mass. Look at the example I cited. I had two different volumes, V1 and V2, but the number of particles I put in here were the same, 6 for V2, 6 for V1, meaning I'm making the number of particles inside constant. So the same number is what I mean by mass being constant. Are you okay?
Yes, please.
Usain Bolt cannot claim to be faster than myself if he's always running on this very good tracks, and my running is done in the mud where the surface is so slippery that I can fall easily. So if for a better assessment of the fact that he runs faster than I do, then we should all be given the same track. Okay, then we run. But if I'm always running in the or like grassy, or this unsuitable field, and he is always training. So that is what I mean by give them the same constant condition. All right, so let's also discuss factors that affect density. Factors that affect density of a substance. Giovanni?
Mass.
So mass affects density. When mass increases, density also increases, provided volume is constant. And what again? Anita, Anna, Priscilla, Godfrey.
Heat.
Yes, so mass, we can also talk about volume. Volume also affects density, and then temperature. Instead of saying heat, use temperature. Yes, of course, temperature change is by the flow of heat. But technically, let's use temperature. Can somebody explain to us how temperature affects density? Can one of our ladies explain how temperature affects density? One of our ladies. Oh, one of our ladies, Giovanni. Are you a lady? Ella, go ahead. Hey, Ella, your voice is so low.
The temperature affects density in a way that when the temperature of a substance increases, the lighter it becomes, but when it decreases, the heavier the substance becomes.
Ella, you are right, but as physicists, we always want you to go deeper and explain why. When temperature increases, the thing becomes lighter. Why? More ladies' contribution. Anita. Anna.
So,
Anita.
so please, when the temperature increases, it causes the expansion of like the substance.
And so
And so the volume increases.
good. That's all that I want. So when temperature increases, the average kinetic energy of the substance increases and therefore increases the volume. And density equals mass over volume. So when the mass will not change when temperature increases, but the volume will change by when heating it would increase. So when V is maximum, density would decrease. And when V is minimum, density would increase. Priscilla, your hand was up. Giovanni, let me hear from Priscilla and then get back.
So I was about to give
the wind is taken out of your sail. Yao pokua. Yeah.
Said this, I was about to give the answer.
Okay.
Sorry.
Then Giovanni, your question. Your hand. Giovanni, your question.
Please say that. So can you say that one of the effects of heat is it changes the state of matter of an object or substance. So if the temperature increases, if the temperature increases, then it changes the state of matter of the substance, causing it to.
Yes, it does that. It does that. You see, when temperature increases, increase in temperature is as a result of the gain of heat energy. So when a substance gains external energy, heat, its temperature increases. And when it loses heat, its temperature also decreases. Okay. And this gaining heat or losing heat can also cause change of state. So heat also does that. And this concept of increase in volume resulting in drop in density is what is responsible for floating of ice on water. Okay, all substances are such that they are solid easily sinks in their liquid. But for water alone, its solid always floats on its liquid. This is because the density of ice is less. And this is due to the fact that as it changes state to solid, it expands and increases in volume. All right. But when we get there, I think we shall get a lot of information about it. Any question? No question. So under fluid mechanics, we'll be looking or going into density the more. That is why I felt we had to review it. As that bad, you also here. And you are quiet. All right. Let's look at upthrust. Upthrust or upthrust or upward force or buoyant force. There are three things which actually mean the same thing. Frank.
Sir, please, can gravity affect density?
Gravity does not affect density. Okay, only mass, volume, temperature. On the surface of the earth, gravity is even constant. It changes slightly at the poles, but the change is even small. We don't even consider it. Upthrust means upward force. Up actually means up. And thrust is a force. So upthrust is upward force. The same as buoyant force. But this is a special force that exists in fluids. So upthrust exists in fluids. Exists in fluids. When we talk about fluids in physics, we are referring to anything liquid and gaseous. So our fluid here refers to anything fluid, liquid and gaseous. Plus, before we even go into upthrust and buoyant force, please, once you started density, let's use the time to talk of relative density, okay? And then we'll take off from upthrust and its cool meanings. We've talked of density, so let's start anything density. We will need it along the way, so yes, in JHS, you learned about how to determine the density of regular and irregular objects. We won't revisit it again. At least that's something you went through in JHS. So determining density of regular and irregular objects. And so let me ask how you determine the density of an irregular object as a form of revision. Yes, how would you determine the density of an irregular object? Okay. Gideon.
Sir, please, you use the Eureka can method, or you can use a measuring cylinder. Try pour enough water into it. Tie a string to your irregular object. Lower it gently into the measuring cylinder. Sir, should I continue?
Continue.
You have to mark the initial volume of water in the measuring cylinder as V1. Then after you drop the stone, or the irregular object, you measure the volume of the rise of the rising water as V2. Then to get the density of the irregular object, it will be V2 minus V1.
Gideon, will that give you the density? Will that give you the density? Class, the question is for all of us. By noting the initial volume, then the final volume, subtracting the initial volume from the final volume, will that give us the density, class? Giovanni.
Sir, please, it will give you the volume of the irregular object.
Exactly. So Gideon, that will give you the volume, not the density. So Giovanni, continue. How then do we obtain the density?
We also have to find for the mass of the object.
How would you do that?
You put it, you measure it, you put it in a weighing scale or something. So when you measure it, you use the formula D, density is equal to mass over volume, where the mass is density is directly proportional to mass and inversely proportional to volume.
Okay,
so then you divide.
Giovanni, you are right. So you must, to determine density, you must weigh it using weighing balance, electronic balance to determine the mass. Then the volume is determined by what you took us to Gideon. So we have the mass as determined by the balance divided by V2 minus V1 as you did, and that would give us the density of the irregular object. As for regular objects, we know you still weigh to get the mass using electronic balance. Then you measure the length, right, and height. This product will give you the volume, and then you divide. Okay. And don't forget that the SI unit of mass density is kilogram per meter cube. Other units can be gram per centimeter cube, gram per millimeter cube. So I'll put questions together under this. So we try and then learn how to convert on Thursday. Let's look at relative density. RD, relative density. relative density, shortened as RD. In physics, when we talk about relative, or when we use the word relative, we are looking at a comparative something with another. So some of the relative stuffs we have RD, relative density, we have relative velocity. In your chemistry, you have relative atomic masses, relative molecular mass. What again? Tell me more. The relative terms and sciences. Oh, that is all. So when we talk about relative density, one, we are comparing the density of a substance, comparing the density of a substance to the density of equal volume of water. To the density of equal volume of water. Okay. Practically, this is Giovanni. Giovanni, hey.
Please, when you take in some textbooks or past questions, they'll tell you that relative density is also the mass of a substance to the mass of water.
Coming. Yes, you are right. I'm coming. I'll explain. So this is Giovanni. Density of Giovanni. Then, because I want to compare the density of Giovanni and density of water, I choose water of the same volume as Giovanni. Okay, so rho of water. But I need to make sure that this chosen volume of water is the same as the volume of Giovanni. Then I can compare Giovanni's density to the density of equal volume of water. But because another way out is that, you see, density is mass over volume. So density of Giovanni equals mass of Giovanni over volume of Giovanni. Then density of water equals mass of water over volume of water. Now, because in choosing the densities, volume of Giovanni must be equal to volume of water. When you divide, when you substitute this for density of Giovanni and of water, you also have mass of Giovanni over volume of Giovanni divided by mass of water divided by volume of water. And RD would be equal to M of Giovanni over V of Giovanni times V of water over M of water. And the two, because volume in each case is the same, relative density would also be mass of substance Giovanni over mass of water. So Giovanni, this is where the other definition you were talking about comes in. So we can also break relative density down to mass, which is mass of substance over the mass of equal volume of water. Equal volume of water. Class, are you okay? Are we okay?
Yes, sir.
Frank.
Sir, please, could you go over?
Oh, don't worry. We are just developing the formulas, so it will be fine. So we have identified so far two relations for relative density. Density of substance over the density of equal volume of water. Then we have, from the density formula, we have also seen that relative density is also mass of substance over mass of equal volume of water. We can also express the same relative density in terms of weight. In terms of weight. And RD is also weight of substance divided by the weight of equal volume of water. We are always choosing volume of water equal as the substance. Then finally, but you see, weight also comes back to mass. Mass of substance over mass of water, because weight is equal to mass times acceleration due to gravity. And because acceleration due to gravity in each case is the same, they will cancel out. So we have mass of substance over mass of water. Please, are we okay? Now the last expression for RD is upthrust in, this time around we are considering ratio of upthrust in liquid to upthrust in water. Upthrust in water. I'll explain this as we look at upthrust and Archimedes' principle. So you get to understand this better later. Now, relative density has no unit. It's non-dimensional. RD is non-dimensional. And so it has no unit, because in all cases, it is the ratio of the same thing, of the substance and of equal volume of water. So RD has no unit, has no unit. we can use determine relative density of a substance using relative density of liquids. Of liquids can be determined using the relative density bottle. By using the relative density, using the RD relative density bottle. Okay, this is formerly known as the specific gravity bottle. These days, it is known as a relative, and it is a very small glass tube. I'll look for the video or the picture and show it to you on Thursday. But the RD bottle is a very, very small glass tube with a stopper, glass stopper. Very, very, very small glass bottle with a stopper fitted at the end. So there's a stopper which is corked into it. I don't know if any one of you has seen that before. The RD bottle. I'll look for the video or picture and then show it to you. It has a stopper. Okay, a glass stopper which is fitted into it. This is the glass, something to represent the glass stopper. Okay, now how do we use it? Yes, Dennis, thank you. Dennis just give us a picture of it on the platform. It's a very small glass. Okay, now how do we use it? We use it to determine the relative density of liquids. Maybe I have petrol, the liquid, or cooking oil. Cooking oil. And I want to determine the relative density using this, the RD bottle. What I first must do is that I must clean the RD bottle with a cotton cloth. Okay, and you must ensure that water thoroughly drains out of the bottle. Then you first weigh the RD bottle when empty. So let weight of bottle when empty be M1. Then you fill the RD bottle with the cooking oil. Fill it, and then you cork it. You put the glass stopper within. There is a hole, a fine hole within the glass stopper, so that there will be overflow of it, of the cooking oil put into the stopper. So you must, when there is overflow, you must clean it so that there is no oil remaining around the bottle. Then weigh. So when you weigh, you determine weight of RD bottle RD bottle and oil. So weight of bottle plus oil. Let that be M2. Okay. Then you pour out the oil. Pour out the oil. Clean it. Clean in and around the RD bottle after the oil is poured out from the bottle. Then you refill the bottle with water. So refill the bottle with water. Bottle with water. Clean it again so that you dry out the overflow of water and weigh. So let the weight of bottle plus water be equal to M3. Let weight of bottle plus water be equal to M3. Now from our record or information, we determine weight of oil alone. Weight of oil. Priscilla, how do we calculate for the weight of oil from our data? Priscilla, if you are there, how do we determine the weight of oil from our data? Priscilla, are you there?
Yes, sir.
And how do we determine the weight of oil from our data?
Okay, so the weight of the bottle plus the oil minus the weight of the empty bottle.
So, okay, thank you so much, Priscilla. So we have M2 minus M1. Your weight of bottle plus oil M2, weight of the bottle alone, empty bottle M1. So M2 minus M1 would give us the weight of oil. What about weight of water? Anita.
Sir, please, the weight of water plus the bottle minus the weight of the
so that
M3 minus M1.
So M3 minus M1. So when you finish, so that's it. When you finish, you use RD being equal to mass of liquid, which in this case is oil, cooking oil, over the mass of equal volume of water. And you see, because in each situation we are using the same RD bottle, the volume of both is the same. So our record would be equal to M2 minus M1 divided by M3 minus M1. That is all. And you have the RD. Now, the moment you determine RD of a substance, you can use that to determine the density of the substance. Because supposing from what we went through, we had RD being equal to 7. an example. If RD is 7, the same RD is also equal to density of substance divided by the density of equal volume of water. Therefore, when you make density of the substance the subject, this is equal to RD times rho of water. RD of the substance, we had 7. Density of water is 1 gram per cm cube. So automatically, it means that the density of the substance is 7 gram per cm cube. So knowing the relative density of a substance, the density can also be determined. Knowing the density, you can also determine the RD of the substance. Please, is there any question to explain? We have 3 minutes to end the show. So this is the whole nitty-gritties of relative density, RD. Okay, we'll go through the upthrust in liquid, upthrust in water situation. Then we apply it to Archimedes' principle and flotation and solving question. You realize that it is a very simple concept. If there is no question, we have just 2 minutes to end the show. Please remind me that next Thursday, we'll be doing teacher evaluation. Okay. So Anita, as usual, be reminding me. Okay. And I have to use about 20 or less minutes to do so. So don't forget to remind me on Thursday. So we'll continue on next Thursday. May the good Lord be with you and then guide you, give you retentive memory. I'll look for challenging questions and send to trial. Okay. All right. So Thursday will be another beautiful day for physics session. Bye-bye and take care.
Bye.
Bye.
All right.
Bye.
Mm.